Abbreviated action. Recall that the usual definition of action is given by integral of time of Lagrangian. This definition is very useful. That's how we get Lagrangian mechanics formulated. However, this usual definition lacks physical picture. We cannot easily identify it with anything that we know. It's some mysterious integral of kinetic energy minus potential energy that is somehow minimized along the true path. There's another way to write action which becomes much more meaningful in terms of physics interpretation. Recall that we wrote Hamiltonian in terms of momentum times q dot minus Lagrangian. This formula that we used is called Legendre transformation. Next, consider that we will vary action, but we do so in a special way. We do so under condition that energy is conserved, or Hamiltonian is conserved. Let's give it a subscript h. In other words, we are not looking at variations around all possible trajectories. We will only consider variations along trajectories that have energy conserved at every point of the trajectory. Then we can write that variation of our integral t1, t2 Lagrangian dt with a subscript h, and we will substitute for Lagrangian the expression in terms of Legendre transformation. Then we end up with two terms. One where we still have the integral, but now it will be integral of p dq dt times dt minus variation with Hamiltonian being constant of Hamiltonian dt. Since Hamiltonian is constant, variation of it will be zero. And so we end up with a definition of action that can now be given only by the first term here, by this term. We will give it a subscript 0 to indicate that this is a special case, so-called abbreviated action, and the integral simply becomes p, and then we have derivative dq dt times dt, which is simply dq. This gives us the definition of abbreviated action. We can still compute variation of the abbreviated action, but now this variation will be along all the paths or all trajectories that have the energy conserved at all points. So this is a slightly different scenario. This formula can be generalized when P consists of many components, say P1 to Pn, as well as Q, generalized coordinate, consists of many components, Q1, Q2, Qn. In which case, the definition simply becomes P vector dot dq vector. Another case worth mentioning is the case when we have periodic oscillations. In the case of periodic oscillations, another case worth mentioning is the case of oscillatory motion, in which case we can perform the integral over just one period. So this is true for oscillatory motion. So what is the physical meaning of abbreviated action? It becomes clear when we consider phase space, say x and p, and whatever trajectory we may have of oscillatory motion. For example, a trajectory that looks something like this. then this integral, as we can see, gives us the area of this loop, which is enclosed by the trajectory in the phase space.